Hello everyone, this is Dr. Fang. This week we will learn Chapter 10, Rotational Kinetics and Energy. Before, in previous chapters, we learned something called translational motion. So from this chapter, we learn another kind of motion, rotational motion. So rotational. So what is rotational? This picture tells you the rotational motion. You have a wheel, right? And then you just spin it, right? So this wheel running, this kind of motion is called rotational motion. There is a fixed point. This is called the rotational axis. This point never move, okay? And anything else will along, rotate around this point. So this is rotational axis. Okay, in this chapter we will talk about how we define a rotational motion. So same as translational motion or linear motion, we will define position, velocity, and acceleration. And then we will learn kinematics, rotational kinematics, okay? And then we will look at the link between linear and rotational quantities. Uh, After that, we'll talk about a very special motions called rolling. So what's rolling? Rolling, it turns out, is a combination of linear and rotational. Combination. You have both of them. And then we'll talk about rotational kinetic energy and the moment of inertial. So we know in linear or translational motion, kinetic energy equal to 1/2 mv squared, right? So what is Kr means rotational. What is rotation kinetic energy of rotational motion? Actually, this is equal to 1/2 I omega squared. Looks very similar. Well, mass here corresponding to moment inertial. So I is moment inertial, and the velocity corresponding to this is a linear velocity v, and this is angular velocity omega. And also we'll talk about last we talk about the conservation of energy. So this chapter basically talk about everything related to kinematics of rotational motion. Okay, so let's define what is how we describe rotational motion. Okay, this is so this picture tells you there is axis, right? Then we let this wheel rotate. Okay, so assume a wheel rotate in this direction. Okay, so how we define position? Okay, well, in linear motion, position we describe position by using a coordinate system. Okay, so like this is a coordinate system, right? And this is orange, and this is the coordinates tells you the position. So you start from here, x initial, right? And you end up here, x final, right? Okay, so position described by coordinates. All right, so now come back to the angular motion. Well, rotational motion also we call that angular motion. How we describe a position? Okay, position described this way. So here is an object, right? So one spot on this wheel. And what is the position of this spot? So what we do here is we draw a reference line. Okay, so this is a reference line. Actually, this reference line is it's random. You can choose at any line. So this line must start from the axis, and it's a straight line. By convention, we just choose um, uh, positive x-axis as a reference line. Okay, so here is the reference line. Always overlap with the positive x-axis. Okay, and then this point we draw another line. Another line link the axis and the point of interest together. So this is another line, right? So this line. So this reference line and this line include the interest point. Okay, so that line uh, is from axis to link the axis and the position of the interest and the interest point. Okay, there are two lines. Then the position described by this angle, the angle between reference line and the line link axis and the interest point together. Okay, so we use angle to describe the position. Remember, this is angle, is not a coordinate, it's an angle. Okay, so angle between reference line and the line link axis and the axial and the interest point together. So the angle between those two lines. And well, what's the unit for the angle? We know unit for the angle in general, we have a degree, right? So the whole circle is a 360 degree. However, the unit for, so we use radian to describe the angle. So theta in radian. Well, radian actually is not a unit. We use a radian to describe this angle. Okay, so this is not a unit. Radian is not a unit. So it is a dimension. It is a dimensionless. Okay. So angle, we describe angle in radian. So what's a radian? A radian here is this. If the whole circle is 360 angle, right? Okay. And what is the radian to describe this angle? Radian equal 2 pi radian. Okay. So the definition of radian, theta in radian, is this. You see, okay, for any angle, it's a circle, right? You have a radius, and you have something called arc length. So this length is called arc length. Okay, so arc length S. Arc length S divided by R is theta in radian. So this angle corresponding to an arc length S, right? And S divided by radius is a theta in angle. All right, so what about the whole circle? Okay, whole circle, and the angle here is 360. What is the angle? What is the angle of a whole circle in radian? So the angle in radian equal to the arc length. So in this case, arc length is the whole circle, right? So basically, this is the circumference of the circle divided by radius, right? So this is 2 pi radian. Okay. So if we want to convert degree to radian, 360 equal to 2 pi radian. Okay. So 1 degree equal to 2 pi over 360 radian, and 1 radian equal to 360 divided by 2 pi degree. Okay, so that's how you convert radian to degree. All right, so this slide tells you basically how we describe that. Okay, so okay, so here we have another unit called revolution. Revolution. One revolution means one complete circle, right? One revolution equal to 2 pi radian. Okay, and also equal to 360 degrees. So you can convert those three different ways to describe an angle. And also by convention. So if you have rotational motion, right? So if suppose this is a disk, rotate along this axle. So this disk either, if you observe this disk either rotate clockwise, okay, clockwise or counterclockwise. Okay, both way. Either you only have two way to rotate, either clockwise or counterclockwise. For clockwise, okay, theta is negative. Okay, and for counterclockwise, theta is positive. And also we define if you rotate counterclockwise, we consider this as a positive direction. Clockwise, negative direction. Okay, so theta bigger than 0 if you counterclockwise rotate from the reference line CCW. Theta smaller than 0 is clockwise, okay, CW. Okay, so this is some definition about the position, right? So if you rotate, start from here, right? So the point is here, right? So you go from the reference line, go to this point, right? So this is negative whatever angle, right? So this angle theta in this case is smaller than 0, and this angle theta is bigger than 0. Okay. All right. And also we might also talk about arc length, right? So what is arc length? So every angle, if you have a circle, every angle will correspond to an arc length. So this length is called arc length. And theta in radian is arc length over radius, right? So arc length equal to r theta. Remember, this must be in radian. Okay. Um, so mathematically, right? So if this angle and you measure the length of this arc length, right? You measure length of that this arc length divided by this radius is the angle in radian. That is very important. So in here we don't use angle. We don't use the degree to describe angle. We must use radian. And sometimes we use a revolution. ReV, 1 ReV equal to 2 pi radian. Okay? So we know angle. We use angle to describe the position of the rotational motion. All right, now, so once we understand what is the position, the rest of that is very straightforward. Well, in translational motion, we know velocity is changing position over time. Okay, so that's a velocity. By the same method, we can define what is rotational velocity, or we call that angular velocity. Why we call that angular velocity? Because you always move through angle, right? So that's called angular velocity, because position is an angle. Okay, so we can, by using the same way, define average angular velocity. Average angular velocity always equal to displacement. Okay, so displacement is final position minus initial position. Okay, so that's displacement. Displacement over time, that is your average angular velocity. Okay, and so we will describe average angular velocity in radian per second. Okay, because radian is dimensionless, right? So this one for the dimension actually is 1 over s. That's a dimension because radian is dimensionless. Okay, so this graph tells you, you see, this is your final position, this is the initial position. The difference here is your displacement, right? Displacement over time. That is the average angular velocity. Okay, so we use omega instead of v. We use omega to tell the angular velocity. Okay, and then same thing here. How we describe angular velocity or instantaneous angular velocity. Same thing. We use average angular velocity to describe instantaneous angular velocity. So here is average angular velocity, right? And then we choose time delta t very small. How small? As possible. Okay. So mathematically, we same thing as we find the limit of the time. Okay. Use the limit of time to 0. Almost 0, not 0. Okay. So this is average angular velocity, and we choose the time period very small, and use this to describe angular velocity, or in general we call that angular velocity or angular velocity. Actually, that is instantaneous velocity, instantaneous angular velocity, Okay, instantaneous means the angular velocity at that instant. Okay, so that is angular velocity. And we already discussed a lot about um, instantaneous velocity before, right? So the same method. Okay, so and the unit for that is radian per second, right? And the dimension here is 1/s. Okay, and also if this will rotate counterclockwise, right? Then angular velocity is bigger than zero. That's just by convention. And if we rotate clockwise, then omega smaller than zero. Okay, so you always just either this will either rotate counterclockwise or clockwise. Okay, so just pick one. Pick one as positive, then the opposite one will be negative. Okay. Um, well, there is another important quantity associated with angular or rotational motion. It's a period. What's a period? Period is a time to finish one revolution. Okay, basically time to finish one circle, right? So suppose you start this point, right? You start this point. This is reference line. Okay, and there's a point. So this is uh, the position, right? And the time. So this guy assume this whole thing rotate counterclockwise. Okay, so start from this point, and the time from here rotate all the way back to its original position. Okay, so this time from to finish one complete circle is called period. Okay, so period is time, right? So time, well, based on omega equal to delta theta over delta t, right? And now what is delta t? Time. Period is delta t, right? Delta t equal to delta theta over omega. Okay, so what is delta theta? You start from here and you finish one complete circle, right? So the displacement, angular displacement here is 2 pi. So one complete circle is 2 pi over omega. So the period equal to 2 pi over omega. Okay, so this is angular displacement divided by angular velocity. Okay, so the time, the period is with a time of, with a unit of second, right? Okay, that is angular displacement, angular velocity, right? For angular velocity, we have average angular velocity and the instantaneous angular velocity, okay, which is also described as, also is called angular velocity in general. Okay, after angular velocity, we will learn average angular acceleration. Acceleration is described of changing velocity over time, right? So average means, well, you see changing velocity and over time. So if just like if you turn the fan on, you see the blade rotate faster and faster, right? So start with omega I, right, and then omega f. Okay, so you know why is it rotated faster and faster? Because of the acceleration. So acceleration, average acceleration equal to final angular velocity minus initial divided by time. Okay, so this is equal to delta omega delta t. Delta in physics is always describe the difference. Okay, final minus initial. So this is the average acceleration, average angular acceleration. We use alpha. Okay, so in almost all angular quantities we use Greek symbols to describe that. So this is alpha. And what's the unit for alpha? Angular acceleration. Unit for that is unit for angular velocity is radian per second, right? Then bottom part is second. So this is radian per second square. And the dimension here is 1 over second square, or 1 over second square, okay? So this is also equal to -2. So this is angular acceleration, and actually this is the average angular acceleration. So same idea. Um, we also have instantaneous angular acceleration. So if we choose a time period very small, right, then we can figure out instantaneous angular acceleration. Okay. Um, so when we talk about angular acceleration and angular velocity, so we have to look at the direction. Okay. So if angular acceleration is in this direction, right? So alpha is in counterclockwise rotation acceleration, then this is a positive. Clockwise, negative. Okay. Um, so here's some example here. Well, angular speed increase. So what happens here is if you have angular velocity in counterclockwise rotation, right? So omega positive, right? And angular acceleration also positive, right? And which means you will speed up. Okay, so you rotate faster and faster. Okay, so you speed up. Or if this is negative, omega is negative, and angular acceleration also negative. Okay, so still you will rotate faster and faster in the opposite direction. Okay, which means if angular velocity and acceleration in the same direction, okay, if they are in the same direction, okay, so omega will speed increase. Remember, it's not a velocity, speed increase. So for this case, right, you rotate, um, so you rotate fast and fast. It's a speed, okay, in clockwise rotation direction, clockwise direction, right? So that's the meaning. So if acceleration and the velocity in the same direction, speed increase, okay? Speed, velocity, say velocity always, velocity is a vector, right? So you can have a positive or negative. Just the sign here tells you the direction. Regardless, just like a remove sign, the value there tells you the speed. So if they are in the same acceleration and the velocity in the same direction, speed will increase. Vice versa, if acceleration and the velocity in opposite direction, speed decrease. So here, this object rotate this way, negative direction, right? However, acceleration was in the positive direction. Okay, so you can tell this will rotate slower and slower. Okay, and the same thing here, if a velocity in this direction and acceleration in opposite direction, and this will rotate slower. So speed decrease, speed decrease. If omega and alpha opposite direction, okay, opposite, S-I-T-E, direction, okay. So this is the same as linear motion. All right. So that's all definition about the angular motion or rotational motion, so everything, okay? And we describe position, displacement, velocity, acceleration, okay? Same as linear motion, right? So here, if angular acceleration is constant, in linear motion, if A is constant, okay, so we have velocity equal to V naught plus AT, right? Same thing here. Because we describe everything in the same logic. If alpha is constant, acceleration is constant, right? So omega equal to omega naught plus alpha t. This omega naught is called initial velocity, initial angular velocity. Okay, so this is the velocity, angular velocity at after time t. Okay, so like this example, so initial velocity is 0, so this guy, right? So this object initial velocity is 0, and this disk here does not move at all, right? So angular velocity equals 0. And if you let it go, so this one move with velocity, the object move with velocity, and this disk will rotate with angular velocity, right? Okay, and we can tell this disk will move faster and faster because this object moving down with acceleration, so this disk rotate with acceleration and rotate faster and faster. So you can later we'll know this acceleration is a constant. So for this object, right, A is constant, and for this disk, alpha is constant. And so we can calculate velocity after angular velocity after a certain amount of time, right? Angular velocity equal to initial velocity equals 0 plus alpha t. So this is 0, right? And give you time, you can calculate, you can figure out what is angular velocity. Okay, and if we compare other things together, so we can use the same logic to figure out what is angular velocity, angular displacement, and basically we have two equations, and based on the two equations we can describe a third one. So if in linear motion, if A is constant, we can figure out, you see, this is a velocity at any given moment, and this is a position at any given moment, right? And so I derived this in class. So you can just we use the same logic, so you can same derivation, and then if we substitute this v by this equation, we can figure out the position in terms of acceleration and initial velocity. And based on those two equations, we can describe the third one. We can derive the third one. Okay, so this is what happened. This is called kinematic equations in linear motion. Because we define everything in the same logic, and so in angular motion, if alpha, angular acceleration, is constant, then angular velocity is this term, and angular position, okay, is this term. Exactly same, you see. You just change all the linear quantity to angular quantity, and the position in terms of initial velocity, initial angular velocity, and angular acceleration is in this term, and bundle 10 to 9 and 10 to 10 equation, we can figure out this equation. Okay, just memorize. If you know how to derive translational motion, then you can use the same method to derive angular motion. Okay, so give me an example. So let's talk about example. So if you turn the fan on, let's go the reverse way. Okay, so here's the fan, right? Assume this fan rotate, doesn't matter, right? So rotate this way, clockwise, omega equal to, well, remember clockwise is negative, right? So negative 20 radian per second. That's really fast. 20 radian per second is really fast. Let's make it, yes, that's fine. And what you do here is you, let's at t equal to 0, right? And so at this moment, you turn the fan off, okay? So when you turn the fan off, you turn the motor off, then the fan keep running. However, you have air drag, right? So assume air drag provided acceleration. Assume acceleration, so in this case, right? Acceleration, because you go this way, so air drag will be in the opposite direction, right? And then alpha is maybe, let's see, 1 radian per second squared, positive, right? So always opposite, okay? And ask you how long does it take to stop? Ask you t when stop, the fan will stop. Okay, so this problem we know omega naught is 0, and omega final is stop, right? So stop, the fan stop. Okay, so ask you T, and also ask you the displacement. What's the angle? Delta theta. This fan rotate from t equal to 0, from t equal to 0 to its stop. Okay, so we just use this all those equations to figure this out, right? So first the time, right? So here we know initial velocity, final velocity, and acceleration, right? So time, we just use this equation, right? So let me write the equation first. So omega equal to omega naught plus alpha t, right? So t equal to omega minus omega naught divided by alpha, right? So omega is 0 minus initially 20 radian per second, negative, right? Remember it's negative. Alpha here is 1, okay? So it's 20 seconds, okay? It's about right. Second, how many revolution or how many radians this fan rotate? Okay, from the moment you switch the fan off to its stop. Okay, so look at the displacement, right? Well, displacement equal to, so we just use this equation, you see, displacement equal to theta minus theta naught, right? So initial position, final position minus, right? Okay, so this equal to omega naught t plus 1/2 alpha t squared, right? Omega naught is negative 20 and times 20 plus 1/2 times 1 times 20 squared, right? 20 seconds. So this is negative 400 plus 200, right? So this is negative 200 radian. Okay, so this fan still keep rotating, right? Rotating clockwise, which is a negative angle, right? And so that is displacement. Okay, well, you can also turn displacement turn radian into revolution. So negative 200 divided by 2 pi, right? So this is revolution, because one revolution equal to 2 pi radian. Okay, so 200 radian equal to 200 divided by 2 pi revolution. So you can figure out how many revolutions this fan will rotate before it stops. Okay, so this is called kinematic equations, and it's very straightforward. We can use this whole set of equations to calculate everything we need. All right, so now let's talk about the connection between linear and rotational quantity. So, so example here is this. You see this guy, right? So you ride on a carousel, right? And this guy, and this is rotational axis. You see this guy will rotate round and round like that, right? Okay, that's a rotational motion. And there is a link between rotational motion and angular motion. Why? Reason for that is this. You see, if we talk about real distance this guy travel, okay? So this guy travel real distance here is, you see, this is real distance, right? Okay. Assume the distance from the XL to this guy is R, okay? So this guy travel actually arc length S, right? So suppose start from here and at here, right? So this guy travel from here to here. So this arc length is the real distance this guy travel. And arc length equal to, okay, theta r times theta. Okay, no problem, right? And then this is arc length. And then if you look at a displacement, right? Suppose you start from here, right? So actually this is, we call it, assume this guy started from here and at here, right? So this actually is delta S, okay? Change in the linear distance and equal to r delta theta, right? So actually this is delta theta. This is the theta I, and this is the theta f, right? Theta f minus theta I is delta theta, okay? So this is angular displacement, okay? All right. So if both sides we divide by time, okay? And the left side is distance divided by time, right? So arc length actually is distance, angular distance, right? Distance in real distance, okay? Divided by time. This we define as tangential velocity. Tangential, tangential in the tangent, right? So this is radiant direction, this is tangent direction. Tangential velocity, velocity in the tangential direction, okay? Right side is r delta theta over delta t. Delta theta over delta t is your angular velocity, right? So equal to r omega, okay? So this actually, we call that a linear velocity. Linear velocity linked with angular velocity by this equation. So okay, so this guy, remember, if this is a disk or this is anything, right? So you may have another person ride the horse here, okay? Um, so everybody will have the same angular velocity because this is the whole thing, whole unit, right? So whole unit will rotate along this axis with the same angular velocity. Omega is the same. However, everybody will have different linear quantity because linear quantity depends on distance r, right? Distance from axle to this position. So this is r, that guy is r, this is r prime. Everybody have a different distance away from the axle, okay? Linear quantity depends on angular velocity times r, okay? Because everybody have a different r, so linear quantity will be different. So on the rim, okay, suppose this is a disk. On the rim, you have a bigger bigger linear quantity, okay? Because r is bigger than somewhere here, very close to this axle, okay? So this guy get a big VT, this guy get a small VT. Okay, reason for that is this R2, this R1, R2 is smaller than R1, right? And the VT2, so smaller than VT1. Both of them have same angular quantity. However, they have a different distance away from the axle, so they have a different tangential quantity, tangential velocity. It is also linear velocity. Okay, so from this example, we know this is your linear tangential displacement, angular displacement. Okay, they're linked by radius. Same idea, we can also figure out alpha. Okay, uh, so we have this equation, right? And then if we look at changing velocity, so changing tangential velocity equal to r changing omega, right? And then divided by delta t on both ends, we can figure out alpha. This alpha is tangential, or we call it angular acceleration equal to r. No, this is no at tangential acceleration equal to r alpha. Okay, so this is alpha. So AT is called tangential acceleration. Tangential, which means acceleration in this direction, in the direction perpendicular to radiant direction. Okay, So if you have something, right, doing, this is called circular motion. You have two acceleration. You have, this is called a tangential acceleration. Okay. Other than that, we already learned in circular motion, you have ACP. We have centripetal acceleration. As long as if you're doing a circular motion, you always have centripetal acceleration. Centripetal acceleration always point to the center of the circle. Okay. Other than that, you also have tangential acceleration. Tangential acceleration equal to R alpha. Centripetal acceleration, right? So what we learned before is V squared over R. V actually is your tangential speed, okay? So tangential speed also equal to R omega, right? Square over R. So this equal to R square omega square over R equal to R omega square. Okay, so this is called centripetal acceleration, tangential acceleration. So this is centripetal acceleration, right? By the way, unit for tangential speed is meter per second. Unit for tangential acceleration is meter per second square, and the unit for centripetal acceleration is meter per second square. Okay, so this is a linear quantity. This guy, centripetal acceleration, also is a linear quantity. Okay, so here is a tangential acceleration. Okay, tangential acceleration I derived, it is equal to radius times alpha. Okay, and so for any rotational motion, you have two acceleration. One is tangential acceleration, which can be zero. If tangential acceleration is zero, then you have, if at is zero, then you have a uniform circular motion. Uniform means the same speed. Speed is same. Okay. Well, speed is same, right? Which means you don't speed up, you don't slow down. Okay. So alpha is zero. Okay. So if alpha is zero, right, then you have uniform circular motion. So even you have a uniform circular motion, you still have centripetal acceleration. Okay. Due to those two, acceleration is in the direction, right? This is in the tangential direction, this is in the radiant direction. So this guy, centripetal acceleration, only changes the direction of speed, and the tangential acceleration changes the magnitude of the speed. Okay, so their response was different things. So tangential acceleration is due to the changing angular speed, and this one, centripetal acceleration, due to changing direction. Okay, because you have two acceleration, two, right? So one is in tangential direction, one is in radiant direction. So the net acceleration, okay, equal to AT plus ACP. You add them together. So this is how you add them together, okay? And the magnitude of the net acceleration equal to AT squared plus ACP squared. And also we can look at the angle, right? So tangent theta here, right? Tangent theta equal to ACP divided by AT. Okay, so you can figure out net acceleration. Okay, if you have circular motion, you always have two acceleration. Okay, so one is in radiant direction, one is in tangential direction. Put them together, that is a net acceleration. Okay, so that's all about the kinematics of the rotational motion. Now let's introduce a very special motion, rolling. Okay, pure rolling. So what is rolling? When you ride a bike, when you drive a car, if you look at your wheel, okay, so this is what happened to the wheel, right? So wheel move forward, right? So this is the motion of the wheel. Okay, just rolling forward. It's called this kind of motion called rolling. Okay, just the roll forward. Okay, um, so if you consider one point, right? So point here, and you can tell when this wheel rotated here, so this point actually will get here, this point, right? So when this wheel get here, this point actually already here. Okay, then the wheel get here, this point will come back to the touch the ground. Okay, so this A got here, A got here, and now A touches the ground. Okay, uh, so the distance, if you look at the center of mass, that's why important concept here, center of mass, right? So the distance, center of mass of, or the axle, this will move here is actually from here all the way to here, right? And what is distance? This distance actually equal to the circumference of this wheel, which is 2 pi r, because the wheel actually rotate one complete circle, okay, and move forward. And the move forward distance is 2 pi r, okay. So we can calculate the linear speed of the wheel. Okay, so because the whole thing, the wheel, even the wheel rotate, however, even the wheel just doing rotational motion, this wheel still move forward by, you see, A from here to A here, move forward by 2 pi r. Okay, so the linear speed of this rolling is v, right? Distance over time. This is the period. The period is uh, time to finish one complete circle. One circle. Okay, so the wheel rotate one circle, right? And that's the time. Okay, so this is your linear speed. Okay, and also we know what is the period, right? Period equal to 2 pi over omega, right? So what is v? V here 2 pi r divided by 2 pi over omega, right? So this 2 pi cancel, so this is r omega. Okay, so this wheel has the rolling of the wheel has two motion actually. You have a linear motion, right? Linear motion with speed, linear speed r times omega, and you have angular motion, right? Angular motion with rotate with omega, with angular speed omega. Okay, so that is rolling. All right. By looking closer, we can tell this is rolling. Okay, so rolling you can separate into two motion. One is a pure rotational motion, one is a pure translational motion or pure linear motion. Okay, so what is a pure rotational motion? Just in your mind, you consider the whole wheel rotate along this axis, doesn't move anywhere. Okay, just rotate along this axis. Okay, so right, so it's a pure rolling. So this is a fixed axis. Okay, then you have pure rolling with angular velocity omega. Okay, so now what is your translational velocity at any point? So this point here is the translational velocity. At this point, translational velocity. This point, this is translational velocity, right? So this is your translational velocity. Okay. And then you have a pure translational motion, pure linear motion, right? Pure linear motion, just in your mind, you consider everything. The whole wheel move forward without rotating. Okay, so this guy move this direction. The same thing here, no rolling. Okay, no rotational motion. Everybody would move with linear motion. Okay, so speed here is forward, speed here is forward like that. Okay, if you add those two together, okay, so you get your rolling. Okay, so talk about what this point is tangential speed. Tangential this speed, right, equal to speed in the rolling, okay, plus speed in translational. Okay, so add together is this is your tangential speed, right? Which is, so this is RW, right? Put together is 2RW. How about here? At that moment, right? So speed for this point from rotational motion is here. Speed for towards left. Speed for linear motion towards right? So they cancel each other. So at this moment, the speed of this point is 0. So we can tell this part, right? So this one, this is for the linear motion. This is for the rotational motion. This is for the linear motion. Put them together. Okay, so this is your tangential speed, right? Same thing here, right? So this is the rotational motion, this is the linear motion, and then add them together. Okay, so that is your rolling. Okay, and you can also think this way. Consider at this moment, right? This is your rotational axis, right? So this point is a tangential speed. This is your tangential speed, right? So this is tangential speed. Okay, so how about this guy in the middle, right? Axis. Axial for rotational motion is 0, right? You don't have tangential speed. For the linear motion, you have this. Okay, so add them together. So the middle point, that is your linear quantity. Okay, all right. So we can use this idea to solve the problem for the pure rolling equal to pure rotational plus pure translational. Okay, you always can decompose a pure rolling. So this is called a pure rolling. Okay, other than pure rolling, you have general rolling. So what's a general rolling? General rolling is like this. Okay, so this will move forward, right? It's not exactly a point contact. You have some other, right? So this will actually, other than rotate forward, you have a slip forward. You have a little bit of slide on the surface. Okay, so that is also happen for a lot of motion, and it's very hard to make that as a point contact with the ground. You always have a slide, like a surface contact, and you have if you don't have a sliding on the surface, then it's a pure rolling. If you have slide on the surface, it is not a pure rolling. Okay. All right. So now let's talk about rotational kinetic energy. Okay. So what is kinetic energy? Well, kinetic energy in general, right? So K equal to 1/2 mv square, right? So you see this is rotational axis, right? And the whole thing rotated along this axis. Okay, so if you look at this particle, kinetic energy of this particle is K equal to 1/2 mv square, right? So this is your V. You have a tangential velocity, right? And we also know tangential velocity equal to r omega. So equal to m r omega square, right? So this equal to 1/2 m r square omega square, okay? And if we put them together, right? So equal to 1/2 m r square omega square, okay? And because we use rotational quantity to describe the kinetic energy, right? So we call this expression as rotational kinetic energy, right? So Kr equal to 1/2 omega square, something in the middle. Something in the middle, mr square, okay? We call that moment of inertia. Okay, moment inertia here is actually it's a rotational inertia. Rotational inertia is not only about the mass, it also depends on the distribution of this mass, right? So distribution means how far away from the rotational axis, okay? So moment inertia equal to mass times the distance square, okay? and which means if you close to this rotational axis, right, moment inertia will be small, very, very far away from the rotational axis. Moment inertia is big. Okay. So this is rotational kinetic energy. So K equal to this term. Okay. Moment inertia. Well, if you have only one object, right? So you rotate along this axis, right? So this is R. 1 point mass, right? Well, the real scenario here is it's not only one particle, right? You have a lot of particle, right? So suppose this is line, and on the line, this is rotational axis O. You have one particle, another particle, another particle, another particle, right? So this is M1, M2, M3, M4, M5, and this guy is M6, right? And distance R1, R2, okay, so on and so forth. And then what is the moment inertia? We know for M6, right? Moment inertia is M6 times R6 squared, right? Same thing here. I5 equal to M5 R5 squared, and one by one. Then ask you what is the total moment inertia. Okay, so you just add all them together. So total equal to, okay, MIRI squared. Just add all them together. Okay. So what if it is a bar? Okay, then you have to use the calculus method to figure out moment inertia. Okay, so that's a moment inertia. Because calculate the moment inertia is beyond scope of this class, you need the calculus method. Okay, so here we just gave you the moment inertia for the object, right? For the solid object. Okay, and the moment inertia also depends on rotational axis. Okay, so suppose you have a ring, so this ring rotate along this axis. What is the moment inertia? The mass of the ring is m, radius of the ring is r, so moment inertia is mr squared. So with this one is pretty easy to figure out. How about a disk? Solid disk, right? So here is a solid disk. Okay, so you rotate here. This is a solid disk, right? You rotate along this axis, right? And then you can separate this solid disk into a lot of ring. Okay, the ring closer to this rotational axis will contribute less on moment inertia, and the ring on the rim will contribute more to the moment inertia. So you average them out, right? The moment inertia of this disk is half mr squared. Okay, and well, if you change the rotational axis, instead of rotate in the middle, if you rotate on the edge this way, this is rotational axis, right? So this disk rotates in that way, you can tell moment inertia will be increased. Okay, so that is the value. And actually, we use something called a parallel axis theorem, and this is really beyond scope of this class. We just let's just skip that. How about a sphere? If it's a hollow sphere, this is the moment inertia, which means hollow sphere, which means this is rotational axis, right? So all the mass will concentrate on the edge, right? So which is pretty big. How about solid sphere? Solid sphere moment inertia will be smaller, okay, kind of average out. And if you choose a different axis, right? So in this case, moment inertia will be big. So in there is a table, there's a big table about the moment inertia of extend objects. So you can, whenever you solve the problem about the moment inertia of solid objects, about any axis, right? You can always look at the table to figure out the moment inertia of that object. Okay, so now let's talk about conservation of energy. Other than linear motion, you have a linear kinetic energy. You also have rotational kinetic energy. Suppose you have an object, right? Rolling forward, rolling. Okay, And if you rotate with omega, you know your angular speed is omega and your linear speed is. So in translational motion, you have this speed. In rotational motion, you have this speed, right? And if you have a rolling, object move forward with translational motion. Meanwhile, you also have pure rotational motion. So kinetic energy for rolling, you have to contain. You have to have two parts. This is your translational kinetic energy, and this is your rotational kinetic energy. Because rolling, you can always separate into translational motion and the linear motion. Okay, and for the translational motion, this is the kinetic energy. For linear motion, this is your kinetic energy. Okay, so do some substitution. Omega equal to well, V equal to R omega, so omega equal to V over R. Okay, so you have, this is the kinetic energy of the object if the object doing rolling. Okay, so you take a mv square out, right? mv square out, right? And then you have 1 plus moment of inertia divided by mr square. Moment inertia depends on the object. Okay, so you have to look at the object to figure out what's the moment inertia. Okay, so what happened here is this. So if you have a ring and a solid sphere, assume they have the same mass and the same radius. Okay, you let them start from the same height, roll down. Which one reach the bottom first? Okay, we can use energy conservation, right? So at the top, you have potential energy, mgh, right? When you roll to the bottom, right, you have kinetic energy. We only have kinetic energy, right? So equal to 1/2 mv square plus 1/2 I omega square, and omega here equal to V over R, right? Okay, that's it, right? So which one move with the fast speed, right? So whoever with the, so we can tell in this case, right? So um, let me see. So from previous equation, right? So this equal to 1/2 mv square 1 plus I mr square. No, mr square 1/2 m. Okay, so this is mr square. Let me see. Wait. That's mr square. Yes, it's mr square. Okay, so put this one out, right? So you can tell you have bottom part have mr square. Okay, and then what is v? So from this equation, m and m cancelled, right? So when you reach bottom, v equal to gh. Let it go. Divided by 1 plus I mr square and times 2, right? And the square root. What does it mean? Which means whoever gets a smaller I will have a bigger velocity. Okay, bigger linear velocity, which means that guy will reach the bottom first. And for this guy, this ring, I equal to mr square. And this is solid sphere, I equal to, if I remember correctly, let's check, okay? Okay, go back. Solid sphere, right? So solid sphere, 502. You see, this one is bigger than the other one, right? So this is bigger, which means this one, when you move down with a smaller velocity. So this guy, solid sphere reach the ground first, reach the flat surface first. Because you know when you reach here, you have bigger velocity. Bigger velocity, which means it take less time. So you reach here. Okay. So that is this is how you solve the problem. The bigger one, bigger moment inertial, right? Because you are on the bottom. So denominator, right? So you make the whole thing smaller. Okay. All right. So that's how you calculate which one reach the bottom first. So to make a summary, so this chapter will describe rotational motion, and everything starts from the definition of position. Position in rotational motion is an angle, okay, and that angle is divided equal to S over R. And once we know the position, then we can describe a displacement velocity. So here is average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. Okay, and then we can use the kinematic equation. So here is a bunch of kinematic equations. It's very similar. And we can also link the linear quantity with the rotational quantity. So even you're doing the rotational motion, you still have a tangential speed, right? Speed in distance, in tangential speed, right? So there's a link between linear quantity and rotational quantity. And you have centripetal, even because you have rotational motion, you always have centripetal acceleration, which corresponding to the position change of the velocity. Okay, and also you have a tangential acceleration. This is the centripetal. This is tangential. Both of them form the A. So net acceleration equal to ACP plus AT. Okay. Other than that, we also talk about rolling. In rolling, you have this term. So rolling is something move forward with speed v and rotate with speed omega. Okay, this is angular speed. This is a linear speed. Okay, they're linked by this equation. Okay, and rotation. This is your rotational kinetic energy. Okay, and here here is the moment inertial because you have only one, not only one object. You have a lot of objects, right? So this is a bar. You can separate the bar into a lot of small part, and the bar rotate along this axis, right? So every part will contribute to moment inertial and add all together. So if those are discrete particles, you do the summation. If those are extend objects, right? So you will do the integral. Anyway, so this is the equation to calculate moment inertial. Moment inertial is about, it's not only about the mass, it's about the mass and the distribution of the mass around that around that rotational axis. Okay, rolling with a slipping, no slipping, right? So this is called pure rolling. Then the kinetic energy, you have two parts because pure rolling we can always separate that into linear motion and rotational motion. So kinetic energy for the linear motion is 1/2 ma square, and for the rotational motion is 1/2 I omega square. And we can also do the substitution. So this also equal to mr omega square plus 1/2 I omega square, right? And this equal to 1/2 mr square plus I omega square. So we can use angular velocity to describe everything, or we can same as previously, right? K also equal to 1 plus I mr square. Okay, to describe that. Both way it's equivalent. So you can figure out this equation. You can figure out linear velocity. By using this equation, you can figure out angular velocity, and they're linked together by v equal to r omega. Okay, and we can use energy conservation to solve the problem. Okay, give you another angle. Give you another conservation of energy problem. Okay, so quickly, problem here is this. Let me just draw here. Okay, the problem here is this. Okay, the problem here is this. You have so now we have so this is a disk, right? And then we want this disk with rope, okay? And then at the end of the rope we have a mass. Okay, so that's a t equal to 0. We set it up, right? Then we let it go. Okay, we let it go. So what will happen? This guy will move down, right? So move down. Okay, so move down. Okay, so this rope will unwind, right? So this guy will down. So assume this guy moved down with 1 meter. I want to know what is the velocity of this object when this guy moved down by 1 meter. Okay, how to solve this problem? Well, we know this is a poly, it's a disk, right? So we know this disk, the mass here is m, radius is r. Okay, so we can use energy conservation. So when you are here, you only have potential energy, right? So this mass m is 1 meter above this position. Okay, so here you have potential energy. Potential energy here is mgh, right? H equal to 1. Okay, and then when this object drop 1 meter, so you have kinetic energy. Meanwhile, this disk also rotate, right? So plus 1/2 I omega square. Okay, and I here is 1/2 m r square. And what's the relationship between omega and v? Omega and v, so you can look at this disk, right? So you have a rope. So this is rope, right? Rope is on the edge of the disk. This rope move down with v, right? And this rope wind around this disk, right? So you can tell rope also doing circular motion, okay, with omega, okay, and also linear motion. And the rope is on the, so the whole disk will rotate with omega, right? However, the rope on the edge, right? So the linear speed for the rope equal to r omega, okay, and the linear speed of the rope here, right? Rope, then linear speed of rope on the disk is r omega, okay, and then the same as linear speed of the rope on other parts. So the object will move down with speed v, right? And this v equal to r omega. So v also equal to r omega, or omega equal to v over r. So you can r, capital R. So you can substitute. So because v and omega, they are related. Okay, so actually this is one equation, one unknown. You can figure out the speed. So this is another conservation of energy. Okay. All right, so that is all about this chapter. Please look at the homework problems, read the book and work on the homework problems, and look at the video I posted on the YouTube about how to solve the problem of this chapter. Okay, so see you next time.